Welcome to session 2 of the ITS Georgia conference. This is going to be on satellite vision. Let's get started with some quick housekeeping slides real quick. So for today's session, if you could turn on your chat for ongoing commentary, use the QA function to submit your questions at the bottom of your screen. To use that, hover over the bottom center of your application and hit the QA button. There's going to be a space there to ask your questions. By default, all of microphones are muted, but you can verbally ask a question by raising your hand using the raise hand button, or preferably submitting a QA request. I will be moderating your session today. My name is Tyler Dickerson. I work for Gwinnett County DOT. First up, we have, before we introduce our first speaker, we have a word from the 2011 time capsule presented by our 2011 time capsule chair, Patrice Keator.
Hello, ITS Georgia. It's Patrice Keator here with DeKalb County Transportation, and I hope your family and yourselves are doing great in this time of COVID, and that your offices are doing great and everything's going well as can be expected. I remember my times on the ITS Georgia board very fondly. It was good times both personally and professionally, and I'm really glad y'all are opening this time capsule. A little history on the time capsule, though. I remember this being Carla Holmes' brainchild. This was her idea, and Marianne Waters was involved, and I didn't want to let either one of them down. So I was tasked with the assignment to create the time capsule, to make it presentable, to make it big enough that everyone could put something in it, to make it a presentation style, to make it durable, and most importantly, to make it cheap. And I remember being stressed out about this time capsule, so I'm really glad that you guys are opening it. Prior to the meeting, they asked us to bring something from our organization or our company to put in the time capsule. But at the meeting, they asked us to write a letter to be read in 10 years. And I did both, and so I'd like to read the letter that I wrote for the Vision 2020 convention back in the day. So, I'll begin. Being the only representative from DeKalb County Transportation here this weekend, I feel a certain pressure to write the right thing, something clever and enlightened. I sincerely hope several things happen before 2020 which will help our industry. Number one, I hope the economy picks up and that there is more money for transportation. Number two, I hope the Transportation Investment Act passes a regional referendum in 2012. May projects improve congestion and stimulate the economy while focusing on sustainability. Number three, more specific to DeKalb County, I hope the county will be a leader in innovative applications related to ITS, and that more funding can be applied to fund maintenance activities so that the cool new gadgets will work after 60 days. As I write this note, I continue to reflect with fondness on the DeKalb County Transportation Signal staff. Tim Sapp, the DeKalb County one, not the Telvent one, although I'm sure he's great too. Charles Fleming, David Smith, Guy Olmstead, Karen Bass, and Herman Fowler. Several will be eligible for retirement before this capsule is opened. I hope they are still with DeKalb County, but if not, I hope they are healthy, happy, and well. I truly believe that this is the best team around, and I'm glad to know and work with them. As for ITS Georgia, it's a good sign if you're reading this letter. I have little doubt that the chapter will continue to prosper because of the great people affiliated with it. I hope I'm around when this time capsule is opened. If not, best wishes, and I have a beer in my honor. Remember, if you can dream it, you can achieve it. Best wishes, Patrice G. Keator. And then I have a PS, and the PS is, I'm on scholarship this weekend. Thank you, sponsors. So the other thing that they asked us to do is bring something that represented your organization, your company, your firm. And I thought about all the knickknacks and gadgets and what I could put in representing DeKalb County. But the thing that meant the most to me was the staff and the people. So I brought a picture, and I'm going to hold it up. It is our DeKalb County Justice League. I'm going to kind of zoom in on the pictures there. You can see their faces have been imposed. And it's just a little thing that we did a long time ago. And it meant so much to me that I actually still hang this on my wall. So this is not from the time capsule. I actually took this one off the wall to show and share with you guys. On the back of that, I wrote, the DeKalb County Traffic Signal Superheroes, left to right, Charles Fleming, Senior Engineer, Michael Parks, Road Design Specialist, retired, Karen Bass, Construction Inspector, Guy Olmstead, Construction Inspector, Tim Sapp, Principal Engineer and Ringleader, David Smith, Senior Engineer, who is at the hospital right now for the birth of his first child. Not pictured Herman Fowler, Senior Engineering Technician, who is too dignified for this silliness. The DeKalb County Transportation Superheroes, a motley crew of extraordinary people whom I am glad to know and work with. Signed, Patrice G. Keator. And I tell you what, I still work with some of these people, but I wish I could assemble that group again. What a great time to be in the traffic signal industry for DeKalb County. I love the idea of bringing government, vendors, consultants, contractors, everyone in the transportation industry to the ITS Georgia group. And I think it's a great organization. Best wishes in the future, and I hope to see you all soon.
Okay, and I'm going to introduce our first speaker for this session is Chuck Michael. Chuck Michael is an accomplished technology innovation thought leader with over 35 years experience in major railroad and mining projects, deep underground high energy physics laboratories in collaboration with the University of California / Berkeley, Fermi National Laboratory, and the National Science Foundation. He currently directs the U.S. feasibility studies for the Hyperloop Transportation Technologies Incorporated, applying skills in transport economics, transportation planning, heavy civic and structural engineering, and project management. He completed his undergraduate studies in civil engineering with graduate studies in particle physics and structure engineering. He is a registered professional engineer in Minnesota and serves as a member of the MIT Technology Review Global Panel. I'll pass it off to you, Chuck.
Very good, thank you, and welcome all. I'd like to thank ITS Georgia for the opportunity to speak with you today. I'm going to talk about Hyperloop, and let me get my program going here. There we go. As he said, my name is Chuck Michael. I'm with the Hyperloop Transportation Technologies. We are based in Los Angeles. We have offices in Sao Paulo, Brazil, Barcelona, Spain, Toulouse, France, and in Dubai, in the Emirates. My role is to oversee all of the feasibility studies in North America, as well as the regulatory affairs. We're going to start today with a little technology background, so you can get an idea of what it is that we're building and the capabilities of that machine. This is a Hyperloop system. This is an elevated section. It consists of two tubes and the capsules that go through the tubes. We start with a tube that is about 4 meters in diameter. We lower the pressure down with a series of vacuum pumps down to a pressure of about 100 Pascal, which means almost all of the air is removed from the tube. And this reduces all of the aerodynamic drag and air resistance inside the tube. The next is the capsule. The capsule is it's designed as an airplane fuselage, although it has no wings and no engine. It has it's a pressure vessel that is levitated with a passive magnetic levitation system I'll get into in a few minutes, as well as propulsion through a linear motor. So since we've elevated or levitated the capsule, we have reduced all of the friction. By removing all of the air in the tube, we have reduced all of the aerodynamic drag. And now with the linear motor, we can propel that capsule up to a speed of around 760 miles per hour. Again, this is the capsule. It weighs about 20 tons. The passive magnetic levitation system was developed by Lawrence Livermore Labs, and we have an exclusive license to that technology. Again, the maximum speed is about 760 miles per hour. Each capsule will hold about 28 to 50 passengers and is capable of transporting around 160,000 passengers per day. Let's go back to the levitation system. This is the fun part. It's interesting that the levitation system requires no energy input at all. The passive magnetic system uses permanent magnets set in a special array, or how we stack all the magnets. This is called a Hallback array. And the Hallback array gives us levitation once we have some movement in the capsule. So as the capsule moves forward, the magnetic field is generated. The magnetic field gives us levitation. And again, we can levitate a 20-ton capsule with virtually no energy input. We recover energy through regenerative braking, eddy current braking. It's an extremely energy efficient transportation system. The infrastructure, there's a variety of applications for the infrastructure. On the left is a typical elevated section. This could be used out in the country someplace or in a highway right-of-way. This is elevated usually around 25 to 30 feet, depending on the bridge standards of the state that we're working in. We have two 4-meter diameter tubes with a cladding that includes solar panels on the top. The second from the left is another urban section. This could actually include walkways on top through an urban area. It also includes some solar panels. And again, the tubes are about 4 meters in diameter. Third from the left is a cut and cover section. This happens to be the most cost effective of all the sections. This is like a shallow berry. The tubes are still 4 meters in diameter, but they do not have to have the structural strength of an elevated tube that spans between pylons. So again, the tubes are about 4 meters in diameter. They could be made of composite material. They could be made of high performance concrete, a number of varieties there. On the far right side is a bored tunnel section. This is what we use when we go into a densely populated urban area. The tunnel bore is around 5 meters in diameter, and with a reinforced concrete segments inside the tunnel, the effective diameter, inside diameter, is about 4 meters. We seal the space between the outside of the reinforced concrete segments and the raw face of the rock to permit or to prevent infiltration of air and water. And in that way, we can go through a densely populated urban area without acquiring right-of-way in terms of property acquisitions. We can go under a city, and in some cases, there are some stations that are designed underground so that there's no modifications to the surface that are necessary. This is what a typical station looks like, around 3,600 passengers per hour. We limit the acceleration on the Hyperloop to about 0.1 G, and we do that because it's a passenger experience, passenger comfort issue for us. There's really, if you're going up to 760 miles an hour, you really don't have to get there that fast because you're going to be faster than anything on Earth as it is. Again, the renewable energies, we can use solar or regenerative braking, geothermal energy, or wind for any of the projects. On the chart on the left is a comparison of energy efficiency, really, between high-speed rail, automobiles, airplanes, and the Hyperloop. The curves indicate that the faster you go, the less efficient you become. The faster you go, the more energy you require. And that's true for automobiles, it's true for high-speed rail, for airplanes. However, for Hyperloop, the faster we go, the more efficient we become. Because of the magnetic system, the magnetic drag actually decreases with velocity. So it becomes more and more efficient as we head towards 700 miles per hour. On the right side is the emissions, carbon emissions, a comparison between automobiles and aircraft and rail and Hyperloop. And this one's an easy one for us because we have virtually no carbon emissions at all. The tubes on the left and the capsule. The capsule has a unique skin. It's designed as an aircraft fuselage, but the skin is what we call vibranium, and we loaned that to the Black Panther, but he gave it back to us. The skin is a double layer carbon fiber that is sensorized. We use sensors all the way through the skin, and that gives us information, continuous information on structural health, speed, locations, anything that we want to know that we can program into the sensors. On the right side, we don't have windows because we're in a sealed tube, although we created our own windows in an augmented reality. And these are programmable windows that you can program if you want to see the Swiss Alps or you want to see cows going by or a cityscape. You can program that into your viewing area. It won't show anything going at 760 miles an hour because your brain really has a difficulty processing that. So we're down in the 65 to 70 mile an hour range to watch the cows. Hyperloop is happening now. It's happening in Toulouse, France. We have built a full-scale test center in Toulouse at an old airfield there. This was completed in 2019. We are doing the testing and certification of our technologies there. We have the integration and optimization, which does take a while. So that'll take us about 1.5 years to finish that. We're about 1 year into it. So we're getting close to finishing everything up to a passenger-ready system. We have a commercial prototype that is under development in Abu Dhabi. The concept design has been completed, and that will be a 3 to 5 kilometer passenger Hyperloop that extends from the expo site in the northern part of Abu Dhabi, as well as close to Al Maktoum Airport, new international airport. On the right side is a cargo program that we've developed in Port of Hamburg in cooperation with HHLA, who's a major port operator there. That is a fully autonomous system, actually, and it's going to be fascinating to watch that system grow. In terms of the regulatory framework, and this is certainly a challenge for any new technology, we have worked with Munich Re, which is the world's largest reinsurance company, and they have helped us develop an insurance framework. And at the end of the evaluation, they determined that our design and the technology is insurable. So now we have that to move forward with. We also worked with a European certification laboratory, TÜV-SÜD, and we have developed, in partnership with them, certification guidelines for a generic Hyperloop system. We presented these guidelines to the European Commission, as well as to the US Department of Transportation as they developed and organized the NET Council, which is the image to the right. This is the Non-Traditional and Emerging Transportation Technologies Council, which combines all of the operating administrations within the US DOT, including Federal Rail Administration and Federal Highway, Federal Transit. In July, they published this document that you see here, the Pathways to the Future of Transportation. This document assigns responsibility for Hyperloop to the Federal Rail Administration, which is significant because now Hyperloop as a technology is eligible for federal funding for planning or for capital grants. And also it has a regulatory home that additional regulatory framework and guidelines still need to be formalized, but it now has a home at the Federal Rail Administration, and we're happy to see that. In the Great Lakes, we developed a major feasibility study that we completed around the first of this year. This connects Chicago with Cleveland and Pittsburgh. This is a major study that it's an open book study. Everything is out there in public. It's been published. It's the only report of its kind anywhere in the world. It's a rather lengthy, about 160 pages. It shows a route from Cleveland to Chicago of 479 miles that we can make in about 50 minutes. Interestingly, this is an extremely efficient, economical project. It has a benefit cost ratio of 2.2, which was determined independently, which really exceeds the OMB requirement of greater than 1.0 to be eligible for federal funding programs. On an ROI basis, it has a 6.5% nominal financial return and 11.8%, which you really don't see in any mass transportation system anyplace, which means this can be developed privately and it will support its capital cost as well as its operating cost. This is the route that goes from Chicago on to Pittsburgh. We start in Chicago. There's 3 routes here, but the blue route is the primary route that we're looking at. There is a connection with downtown Chicago as well as Midway Airport. We head to South Bend, Indiana, to the Toledo Airport, into the Cleveland Hopkins Airport, and then into downtown Cleveland, where I think we'll probably diverge onto this white line, which is the hybrid route, which takes us into Pittsburgh International Airport and to downtown Pittsburgh. Let's back up just a minute, because the obvious question is, how much does this cost and who's going to pay for it? We did a cost estimate that was evaluated independently. It comes out to about $55 to $60 million per mile for comparison. Other technologies, other areas of the country see different cost ranges, but that is what is published in the report. In terms of the economic impact, it's significant. Those of you that work in transit-oriented development know that when you have a station nearby, especially a major station in a major metropolitan area, there's significant real estate development and jobs that come into this area. So we have around $47 billion in increased income, $74 billion in property value increase, and around $12 billion or more and expanded tax base for local, state, and federal taxes. One of the secrets to the organization of this project is really a partnership. And we started about a year early, before the feasibility study was initiated, developing a consortium of those that are interested in seeing the Hyperloop developed in their region. We have about 80 members of this consortium. It's called the Great Lakes Hyperloop Consortium. It includes MPOs, DOTs from 4 states, Pennsylvania, Ohio, Indiana, and Illinois. Actually, the DOTs were funding partners, as were the tollway authorities in a couple of states. Other funding partners included the regional MPO in Cleveland, Northeast Ohio Area-Wide Coordinating Agency, the Richard King Mellon Foundation out of Pittsburgh, and the Cleveland Foundation in Cleveland, Ohio. So with all of these stakeholders, with a common goal in mind, we organized a series of technical advisory committees, and we worked closely with the Net Council and the US DOT in organizing the overall project. So we sat down with the FRA, the FTA, Federal Highway Administration, and so forth. The pipeline people were there, Federal Highway. And as we organized these technical advisory committees, one in Pittsburgh, one in Chicago, and one in Cleveland. The interesting one in Cleveland, or in Chicago, by the way, is that all of the Class 1 railroads in that area were part of the technical advisory committee. We had a great discussion with them about using railroad right-of-way. We can go underground or we can go elevated up to the extent that we wouldn't interfere with any of their traffic. And the same is true on interstate highways, state highways, that the right-of-way could become available if it's straight enough for us, with the one condition that we don't interfere with any of their duties or the flow of transportation or safety. The feasibility study results, as I said, the feasibility study itself was performed by TEMS, Transportation Economics and Management Systems. They're a transport economist out of Maryland. Hyperloop TT did not retain them. They were retained independently by the MPO and reported to the MPO. So these are independent evaluations of our technology, and they developed a lot of the business case and the economics surrounding that, as well as the potential routes. So it was a great partnership. We set up a P3 actually with the MPO. So Hyperloop TT and the MPO organized a public-private partnership, and then the MPO retained the consultant. And now I think we're just about to the end. Happy to take any questions that you have. I'll turn it back to Greg.
Okay, since Greg's not here right this second, what is the development cost per mile urban versus rural? What R/T fare was used for that financial BC analysis?
The development cost in urban versus rural, a lot of the urban was done in a bored tunnel, like under Chicago and under Cleveland and Pittsburgh. So that's going to have a little bit higher cost. The cost for a bored tunnel is probably in the order of 60 to 65 million a mile. Keep in mind that these are small diameter tunnels. These are not large ones that you could drive a car through, or for an automobile tunnel or a rail tunnel. In the rural areas, the most cost-effective section was a shallow trench, and that came in at around a little over 30 million per mile, because we didn't have pylons, we didn't have foundations, we didn't have deep boring, we didn't have to have a structural steel tube. So that was the most cost-effective, and it allows the project to be built across like a farmer's area, that we would not interrupt his farm plan, and they could still get paid an easement for that. In some cases, we would go elevated, and the elevated will run probably around 50 million per mile. What was the next question?
Any ideas on a round trip fare yet?
Oh, we think it's about the same as a bus ticket. The interesting thing with the Hyperloop is that there's a passenger market, which is significant, but also significant is the light freight market. And these are the parcels, these are the high value, time sensitive deliveries, whether it's pharmaceuticals or other medical supplies, airplane parts, and so forth. So all those parcels that we get delivered to our door every day by Amazon have to come from a fulfillment center, and the most cost-effective way is through, we believe, through a Hyperloop. It's really taking that market from the air cargo and bringing it down to the ground in a more cost-effective way.
I'm actually going to follow this up with one more question here. Is there a local or express option, and would there be several stops for every trip?
It's a good question, because it's a point-to-point service. You buy a ticket, if you're in Pittsburgh and you buy a ticket to Toledo, you will go nonstop. There's about 28 to 50 passengers per capsule, and they will once you get on the main line, if you will, if there's a station, it's an offline station. So the capsule will go off the main line and slow down, go into the station, and the through traffic will continue on without having to slow down or to stop. So it is a point-to-point system with smaller capsules than you would see normally in a train that would have a consist of maybe 180 passengers, 200 passengers or more. So it becomes a very cost-effective routine as far as the scheduling and the getting off the main line into the stations. It's not a scheduled service per se, it is a demand service.
Okay, thank you, Chuck, for giving all the information to us. It was really informative. At this point,
Thanks, everyone.
We now have a word from our platinum sponsor, Arcadis. Okay, so now we're going to move on to our second panelist today, Raj Ponnaluri. Sorry. Raj is the State Connected Vehicles, Arterials, and Managed Lanes Engineer at the Florida Department of Transportation. In addition to leading the state's Connected Vehicles, Arterial Management, Managed Lanes, and Connected Vehicles programs, he assists with the development of the TSMO initiatives. He holds a BSCE, MS, MBA, and PhD in Transportation Engineering. He is registered PE, PTOE, and PMP. He has over 25 years experience in traffic engineering operations, ITS, TSMMO, CAV, and WWD, public transportation, and projects and contract management. Raj has published his work with several journals as well. Raj, I'll let you take it away.
Thank you very much. I really appreciate that. I'm going to now go ahead and start sharing my screen. Good afternoon, everyone. It's a pleasure to be here today and speaking at this ITS Georgia meeting. Are you all able to see my screen okay? All right, okay, so why don't I get started? As was introduced, my name is Raj Ponnaluri. I'm the state's Connected Vehicles and RTL Management Engineer at the Florida Department of Transportation. I'm also the state's Managed Lanes Engineer. Today I'm going to take no more than 15 minutes, hopefully. I just checked my clock, so hopefully I won't take more than 15 minutes. I want to present to you the Florida DOT's CAV program, or the Connected and Automated Vehicles program. Some of you may have heard some of these topics before, but I really want to emphasize that this program is continuously evolving. It changes by the day, not by the week or by the month, so to say. So everything we do is updated on a regular basis. So what you're seeing is the latest and the greatest information that I have at this point in time. Why exactly is Florida embracing emerging technologies, especially connected and automated vehicles? Well, plain and simple. As you see on this slide, it is all about Vision Zero, essentially. In other words, how can we actually work towards minimizing, I should say, actually mitigating and eliminating all road traffic crashes. Here in the state of Florida alone, during the year 2019, if we take the latest numbers, there were more than 3,200 traffic fatalities, and 700 plus of them were actually pedestrian fatalities. And if you take 365 and divide with 718, just under 2 pedestrian fatalities happen every single day of the year here in the state of Florida, which is not something anybody will ever be proud of. This is not a good statistic, and we want to address these concerns. I can go on and on explaining the importance of why safety is so important to all of us. We also see emerging technologies as playing a role not only with improving safety, but also with reducing traffic congestion. I'm sure many of you have heard of this statistic which says that 94% of traffic fatalities are due to human error. Even if half of that is true, then obviously technology has a significant role to play. So what are the CAV elements? When we talk about connected and automated vehicles, what exactly are we talking about? Well, strictly from a components point of view, we hear about roadside units, we hear about onboard units, we need a good communications network, we need good traffic signal controllers, we need a good ITS system, the fiber optic backbone. There's many components that truly go into making a CAV program successful. And when it comes to data, there are numerous data types. I'm not going to enumerate all of them, but the point that is being made here is that CAV is a combination of many things. It is about the CAV technologies, it is about CAV equipment, it is about CAV data types, and last but not the least, it is also about the type of applications we're going to choose. Are we interested in moving transit through a system, transit signal priority? Are we interested in moving freight through our roadway network? Freight signal priority is a good application. Are we talking about having the emergency vehicles move from point A to point B with minimal to zero friction in the system? Emergency vehicle preemption. Bicycle pedestrian detection is another one. We all hear about SPAT map, etc. So there's many ways of thinking and looking at CAV. I'm just trying to present to you that there are many standards that are relevant to CAV deployments. I'm not going to list all of them, but there's numerous things that are happening in the CAV technology as of today. When it comes to automated driving assisted systems, there's always the question, should state DOTs and public agencies invest in these technologies? Well, it is as simple as this. When it comes to 94% of traffic crashes that are due to human error, we've always tried seat belts, we've tried airbags, we've tried the traditional traffic engineering technologies, but we know that there's a role for these emerging technologies. For instance, many of our cars already have, many of our vehicles already have the lane keep assist. Blind spot warning, I'm sure many of you have your vehicles with blind spot warning. I'm sure many of you see a benefit to that. I have seen personal benefits with a blind spot warning, and I should say eliminated a potential crash that would have happened to me because of a blind spot warning. I can go on and on. In other words, we all personally experience the role of technology in addressing safety and also improving mobility on a regular basis. The question is, why don't we expand and scale them up to improve safety and mobility overall in our transportation system? I said enough about safety and mobility, but connected and automated vehicles also have a role to play with economic development. Our elected representatives, our leaders, truly want to have economic development in our respective states. And that means to bring about workforce development, we need to have technologies too. The new young generation are interested in technology and they want to work in an environment where technology is very much at their fingertips. The point once again is that when emerging technologies are here, why don't we embrace them and implement them to improve safety, mobility, economic development, and also from an environmental friendliness standpoint. So to accomplish this, Florida DOT has embraced the concept of developing a business plan document. We have the TS-M&O strategic plan, which we adopted 2.5 years ago. Then we went about developing the CAV business plan, Connected and Automated Vehicles Business Plan, which was adopted just under a year and a half ago, just about a year and a half ago in the year 2019. There are 7 focus areas, as you see here. Policies and governance is one of the first ones. In other words, we need to have the leadership support. We need to understand the priorities with the leadership. What kind of policies need to be adopted with complete streets? What exactly is the leadership wanting us to do? So understanding the policies is an important process. Setting the right kind of organizational framework, in other words, a governance system, is important. And when you have a good policies and governance approach, that is when policies funding becomes easy. In other words, program funding becomes easy. Education outreach is important because in today's world, as you start embracing new technologies, everybody would be interested in knowing whether these technologies are safe, whether our roadways should in fact allow vehicles to operate in an autonomous mode. So it is important to talk about the role of technology, the risks we face, how to mitigate them, how to address them. So education and outreach is all about sensitizing the general population and the drivers and the people and road users about what these technologies can and cannot do. We should also be realistic. We should not promise anything that is not doable. Sometimes we think that these technologies are going to solve all the problems. Not necessarily. Technologies do solve a lot of problems, provided we consider the risks and find a way to mitigate them. At the end of the day, state DOTs like Florida or Georgia, GDOT or FDOT, we all have to work with the industry. And that is because public agencies know what is in the public interest, safety and mobility, for example. On the other hand, it is the industry who are constantly innovating and bringing solutions to all of us to make sure these things do in fact happen. So industry partnerships and outreach are absolutely key. When we do all these big things, let us not forget that developing the right kind of technical standards, the specifications, and the appropriate documentation is important, especially when it comes to emerging technologies. So that is another focus area we have identified. Implementation readiness. I do not know how many of you would agree with me, but apparently some statistic out there which says that less than 20%, 1 in 5 traffic signals in the country today are emerging technology ready. Here in the state of Florida alone, we think that under 40 or 45% of our traffic signals are emerging technologies ready. In other words, we need to understand whether our roadways, our infrastructure, our ITS systems, our traffic engineering systems, our traffic signal controls, etc., are we ready to deploy these emerging technologies? If we don't, what kind of gaps do we identify? So implementation readiness is absolutely key. And last but not the least, there's nothing that is going to happen without good deployment and implementation. If you look at what Mr. John Hibbert does in Georgia, right? If you look at what Alan Davis does, what Andrew Heath, these folks actually are really the pioneers in the country today when it comes to emerging technologies. And GDOT is in a great spot with the kind of work that's happening. Let's quickly talk about the technology-focused projects here in the state of Florida. This is a particular web page that is available, publicly available. All you have to do is go to Google and type FDOT space connected vehicles. And one of the first 2 links that comes up is this. The other one is the business plan. So as of last week, or as of this morning, I should say, Florida has about 28 major initiatives that are in various stages of planning, design and implementation, and some projects are already operational. You will see some major projects on this list. For example, the I-75 frame project. I'm going to talk about that in a few minutes. I-4 frame project, which won the ATCMTD award recently. I'm going to talk about that briefly. Statewide security credential management system platform. I'm going to talk about that as well. So if you look around the state, there are numerous projects in all the 8 districts of the Florida DOT. Many of them are Florida DOT led. Some of them are in partnership with others. You see projects like the AV shuttle. You see projects like the SPAT and MAP efforts that are being deployed. You look at the Smart Road Ranger project that is being discussed. So there are numerous initiatives that are underway here in the state of Florida, not to forget the SunTrax system, which is being developed by the Florida Turnpike Enterprise. I'm sorry, this map is not very clear. I apologize for that. But there's 3 SPAT projects that are being displayed here. One is in Tallahassee, right here in Tallahassee, not far from Georgia. As I look on the other side, the Gainesville Trapezium is another project. That's a second SPAT project. And the third SPAT project, which you can't see properly, is the Pinellas County SPAT project just south of Tampa. All these projects are different from each other. Tallahassee was just a plain vanilla SPAT and map. Gainesville had a value add, which is bicycle pedestrianization, passenger collision warning, emergency vehicle preemption, transit signal priority, etc. Pinellas County, on the other hand, would probably experiment. I say probably because we're deploying it as we speak. We're going to have dual mode RSUs from CAPS, and Gainesville is actually Siemens project. So the CAPS project is going to have a roadside unit with both CV2X and DSRC. So we'll see how that is going to work. Quickly moving on to the frame projects. As I said earlier, one of the first frame stands for Florida's Regional Advanced Mobility Elements. This project was conceptualized about 3.5 years ago, which goes between Ocala, just north of Central Florida, and goes all the way up to Gainesville in Alachua County, 75-mile section of Interstate 75. This project has gone through all the systems engineering development process. 2 contractors are on board. The project is being deployed. We're looking at 200 plus roadside units with DSRC capabilities. We are also talking about freight signal priority in the southern area, which is Ocala. In the northern, in Gainesville, it's going to be mostly bicycle pedestrian work. So there's a lot of work that is underway. And this is consistent with also the University of Florida bicycle pedestrian project about which I did not touch. I-4 frame project is the ATC MTD award project. It runs from Orlando to Tampa, 75-mile section. Queue warning, speed harmonization, integrated corridor management, adaptive signal control technologies, the whole 9 yards, basically to address not only the interstate issue, but also the elements when it comes to traffic signal systems with freight signal priority, wrong way driving, etc. The US 41 frame project is an arterial frame project in what we call the District 1 region in the Fort Myers, Naples area in South Florida. This one is also mainly aimed at ICM, integrated corridor management, except it is on the arterial system. I'm not going to say much about the V2X Data Exchange platform because this project is in the procurement stage right now. This is an $8 million effort. This particular initiative is going to do 3 things. Number 1, the project is going to connect to all the roadside units in the field and bring the data back. That's 1. Second thing it does is to analyze the data, collate the data, connect with SunGuide, Florida 511, etc. So a lot of back-end analytics, both for historical and real-time analysis are performed. And the third thing it does is it packages the data and distributes the data to anyone, particularly car companies and auto OEMs, with the expectation that these data would become a part of the vehicle CAN bus, and that way avoid the situation where we have to purchase hundreds of thousands of onboard units. We'll see how this project goes. This is an interesting one going forward. We hope to complete the selection by early part of 2021, which means by mid-21, we should be having some news on how the project is progressing. The other initiative we just completed is the security credential management system. When I say completed, deployment is just completed. We are still working on bringing all the projects into the Sems platform. So this project was procured as of, I want to say, February or March, and we are well into deploying it more or less completely in the state. We are already having several projects, the SPAT projects that are integrated into it. As many of us know, an Sems platform is one which is going to work towards securing 2 things. Number 1, the message content and the source of the message. It verifies for these 2 elements in particular. I'm not going to bore you with all these details on IEEE standards, etc. But the bottom line is this is a part of a larger cybersecurity framework which we want to get into, physical electronic security of the not only the data, but also the infrastructure, and also building a platform which is going to give the confidence to all the folks who are out there who want to implement the CAV systems. I have 1 or 2 slides and I'm done. With the outreach initiatives, Florida DOT has carved out $10 million for what we call TAPS LA, which stands for Technology Applications Partnership with Local Agencies, $2 million per year. This is the approach where Florida DOT will work with the local agencies to see that projects that are implemented would be beneficial both to local agencies and Florida. iStreet program, on the other hand, pardon me, iStreet program, on the other hand, is a research and development type of initiative where we are going to work with the industry and where we're going to put projects on the street, competitively procure them, and implement these projects in such a way that we have an opportunity to conduct the before and after type of analysis and learn the lessons for future deployments. With that, I think I kind of hit the 15-minute mark in a way. I just wanted to say thank you very much for the opportunity to present to you all, and I'll be happy to take any questions.
Thank you, Raj. We do have a first question already. What are the measures of success that have been defined for your CAV program?
That's a very good question. I really say that's a great question because this question always comes up. Let me just go a little, first of all, let me answer the question. Clearly, safety and mobility would be the high level standpoint. In other words, when we deploy these technologies, are we in fact going to actually see a reduction in traffic crashes? It is one thing to say that deploy the technology, you'll see a result. It's a whole different thing because so many of these technologies are emerging. We're all learning a lot of lessons. To answer the question very directly, I would say, if we can have a certain percentage reduction in traffic crashes, some crashes may drop as a result of technology deployment. I'll give you the example of bicycle pedestrianization. Let us take the simple situation where, as of now, today, motorists have to go push a button to be able to cross a traffic signal at a traffic signal, or even at a mid-block crosswalk, they have to push to get the RRFBs to start flashing. Imagine a situation where it's happening, by the way, you don't have to imagine, it's already happening. But let us say we deploy a CAV program, a project within the CAV program, where we have passive detection of these pedestrians. So a pedestrian is detected passively. They did not push the button, but the system, actually the traffic signal controller, places the call for the next best opportunity to have the pedestrian cross the street. Or at an RRFB, we can start flashing. Just the other day, I saw on LinkedIn, the Federal Highway Administration's note that many of the pedestrian crashes occur when there is no street lighting. That is so true, actually. Many of the, if we go do some quick analysis, we'll find that to be the case. Anyway, long story short, that's, in my opinion, are we seeing a drop in the percentage reduction in traffic crashes? All right. Well, we deploy the technologies. We are able to warn the motorists about the length of the queue, the speed at which the back end of the queue is moving, and therefore give information in advance. Are the secondary crashes dropping 2 years or 1 year after deploying these technologies? Another measure. Are we able to clear the incidents sooner? Do we have fewer incidents as a result of this? On a road ranger system, when we deploy this technology, are the road rangers able to respond quickly and sooner than they were used to doing? There's clearly some ways of handling this situation going forward, but this is an area which continues to evolve. As of now, we all can take our guess. We all can take our best guess, but it is only the near future which will tell us what these measures are going to be. Great question.
Currently don't have any more. Thank you for your time today, Raj.
No problem. Thank you, Tyler.
No problem. I'm going to start introducing our next two presenters. Mike Clance is a Q-Free America's engineer sales manager, urban solutions, and supervises the daily operation of the company's projects across the eastern portions of North America. Mr. Clance has more than 30 years of experience as a software engineer, solutions architect, systems integrator, project manager, and project manager. In these roles, he has been responsible for managing software development projects and software engineering teams, both locally and internationally. He has also been responsible for managing customer relations and delivering and implementing software development projects for these customers. Mr. Clance has been a leader of software development teams, testing, and system integration, installation and integration teams for traffic management software. He has extensive experience in system design, software design and development, system integration, and troubleshooting and debugging. Mr. Clance graduated from Oglethorpe University in Atlanta in 1988 with a bachelor's degree of science. He is a current member of ITE and ITS America and is involved in several transportation research board committees. Our second presenter is Lehrke, who works for Minnesota DOT. With his work, he works to manage the advanced traffic management system and optimize the 700 plus owned Minnesota DOT metro area signals. He also has deployed and configured several automated signal performance measurement software in conjunction with state-of-the-art non-intrusive detection systems to monitor our signal networks and identify their maintenance issues. He provides input into the design of new signal systems to help with construction management all the way through the signal turn on. His work includes upgrading, designing, and maintaining remote Ethernet communication infrastructure to allow real-time communication not only to the traffic signals, but to all the other signal cabinet devices as well. Mike and Derek, I'll let you guys take it away.
All right, let me share my screen here. All right, I hope everyone can see that. Thank you, Tyler, for that introduction, and thank you to ITS Georgia for the opportunity to present today. Derek and I are going to talk about a subject called Free the MIBS. The core of this is the goal of expanding protocols and interoperability for devices used in our transportation systems. As we look to the future and the new technologies coming, some of the technologies that have been described by Raj and others, we really need to look towards the ability to have these devices communicate with each other and to have systems communicate and share data with each other. So that's the topic we're going to touch on today. We'll talk about NTCIP and MIBS. Those are terms that a lot of people have probably heard. You may know some about these topics. You may be totally clueless as to what these terms are. So we're going to start out with a poll. Tyler, can you put that poll up, and let's give everybody a minute or two to pick the right answer. So hopefully you guys can see the poll and you're selecting your answer there. Just give us a little bit of indication of what you know about MIBS. Tyler, anytime you're ready there, we'll see the results, and then we'll move on. Okay, so we've got our results now. Looks like the most popular result is this not the snack room? So a lot of people have indicated that they know a little bit or not much at all about MIBS. Well, hopefully today, after this session, we can change that a little bit, and you'll be able to say you know more about NTCIP and MIBS. So let's move on. Before we can really dive into NTCIP and the MIBS, we need to talk a little bit about the past and what things have been like in our industry. In the past, transportation systems, signal systems, dynamic message sign systems, early transportation devices were deployed with unique data definitions and unique, most of the time, proprietary communications protocols. What that meant was that devices and systems from one manufacturer could not communicate with other devices or even the same devices from other manufacturers. So you had these siloed systems in which you could not share data. Oftentimes, if agencies wanted to be able to share data between these systems, they had to engage in costly custom software development. So a lot of money was spent trying to make these things work together. And you can imagine in today's environment, as we have more of these devices out there in our transportation systems, and we have more data being collected, being siloed is just not an efficient means of operation. So where did we go from that? In the early 90s, MEMA, AASHTO, and ITE started developing the NTCIP standards. And they had a joint committee that agreed to develop these standards for different devices that would set up the communications protocol and the vocabulary or object definitions for each device. And that would allow now for devices to communicate with different systems so that we could share information, so that agencies wouldn't be locked into solutions from one particular vendor. That's where we got started. In '96, AASHTO and ITE started this joint committee, and they then developed several different standards. You see here a list of some of the more prominent NTCIP standards. 1202 defines the actuated traffic signal control protocols and objects. 1203 is used for dynamic message signs, and then you see some of the others, 1207 for ramp meters and so forth. This list is continuing to grow even today. But what these standards do is they define each object with an identifier and with a range of values that the devices will support if they're going to be NTCIP compliant. And you can produce from these standards a MIB, which is simply a text file that contains the definition of each object that the device supports and its values and how you access that information, how you write new values to it, how you read values to it from it. So that's what the MIB is. It's just a simple text file. It can be read by humans or it can be compiled compiled by computers into different applications. So what did we end up with? Well, when that was done, the NTCIP standards had objects that were defined to be mandatory. In other words, if you're going to have a signal controller that is NTCIP compliant, it must support these objects. But the NTCIP committees left room for different vendors to add what are called proprietary objects to their devices so that they could implement different functionality and then have different objects in it beyond the standard, beyond the mandatory. So what does that mean? It means that a device could be fully compliant with the NTCIP standard, but not work with an NTCIP compliant system because the functionality was put into these mandatory objects or into the proprietary objects. Vendors would treat these proprietary objects like a proprietary protocol, not share it with others. So we really weren't much further along than we were with the original proprietary systems. Agencies were getting locked into one vendor's solutions for the life of their system. They bought a vendor's hardware. They would have to buy that particular vendor's software in order to use their devices to the greatest extent. Overall, what it did was it served to stifle innovation and to put a clamp on data sharing. So we couldn't bring our systems together. Agencies couldn't pick a different software package that might provide better functionality because they were locked into the support for the proprietary NTCIP objects that for their devices they had. What else happened? Well, as technology changed, as technology improved, as ideas on how to better manage traffic were developed, we went beyond the standard, and the standard was slow to change. And a perfect example is the flashing yellow arrow on a traffic signal. There was no support for that in the 1202 standards version 2. So many vendors developed their own proprietary objects to support the flashing yellow arrow. And those objects all differ from vendor to vendor. The standard, meanwhile, was taking years to update and years to catch up. So different vendors have all implemented this separately, and then systems can't support vendor B's system may not support vendor A's devices for the flashing yellow arrow. So we're stuck in this situation where innovation is really kept tamped down, and we can't bring that new technology to our market, to our industry. Looking at the numbers, if you look at a modern traffic signal controller, there are over 1,000 NTCIP objects defined that make available the data on that controller and allow you to set the parameters that then control the operations of that controller. Of those 1,000, about 75% of those objects are manufacturer specific or proprietary. They're not the standard mandatory objects. If you look at the two standards that affect a signal controller, 1201 and 1202, they only define about 350 objects. So you can see there's a lot of functionality there that can't be accessed by a third party to show support for a particular device. So what has happened? Enter Free the MIBS. Free the MIBS is a collaborative campaign by the industry, started for the industry to encourage not just traffic signal controller manufacturers, but ITS device manufacturers to share their complete MIB definition for their devices, to make it open to the public so that third parties can implement support in their systems for these devices and provide our customers, the public sector agencies, the greatest number of options for selecting the systems and the functionality that they want there. You can see here the logos for a number of the devices, a number of the vendors who have joined Free the MIBS. Q-Free was a founding member, of course, of Free the MIBS. Siemens has joined this year, and APC and NCOM have both joined either late last year or early this year as well. And you also see Oregon DOT and Utah DOT have been early advocates of the Free the MIBS movement, and have been encouraging vendors who do business in those states to openly share their MIBS and to join this organization. So we do meet some resistance. We do meet some objections to our MIBS, and I just wanted to talk about a couple of those. Some common misconceptions that are sometimes used to greet our message of openness and sharing data. The primary one, MIBS sharing is going to make you more susceptible to cyber attacks and threatens intersection safety. That's totally false. NTCIP itself is an inherently insecure standard. It's a serial-based protocol that can be sniffed and manipulated. MIBS can be reverse engineered, and as well, the critical functionality of a controller, things like your green times and your yellow times and your red clearance, are all defined in the mandatory objects, which are publicly available from the NTCIP website. So making the full MIBS with the proprietary information available does not increase your susceptibility to cyber attacks. What we as an industry need to do is follow the lead of others like the financial industry and implement current data transport standards, security standards, to make sure that our network communications is more secure and protected, so that people can't launch these cyber attacks. The next objection we often see is sort of an extension of that sharing our MIBS is going to result in improper or potentially dangerous use of these devices. But again, that's false. If we go back to our response to the previous objection, the functionality, the critical functionality of the controller is contained within the publicly available MIBS already. So you're not providing additional information that will make the device more susceptible to dangerous use. But that's from my point of view, from the Q-Free point of view. I'm going to turn it over to Derek now, who's from Minnesota DOT, and let him provide a public agency perspective. Derek?
Thank you, Mike. So as I said in my bio earlier, I've been working with the Minnesota DOT since 2017, and since then we've developed or deployed a much more advanced ATMS system than what we currently had. And one of the first things that we ran into was basically this MIBS sharing issue. So unfortunately, with how our system was deployed, we ended up selecting through an RFP process different vendors' ATMS system than our current controller manufacturer for most of the signals in Minnesota. So this MIBS sharing helps to reduce all this vendor lock-in, where normally if that one vendor is supplying a signal controller, they only have one signal controller, one type of detection, one type of APS system, and it kind of really locks you into that particular vendor, since you kind of want to keep everything simplified. But it also reduces the competition between those different vendors. So what we've seen since we started deploying the ATMS system, in starting to deploy multiple different manufacturers of controllers, is we are starting to see that competition play a role. We're seeing different features being added into the controllers, and a much more responsive Mike, I think you're bumping back there we go. We're starting to see them increase, that competition increase, to where features that we want deployed into the controller where they used to not go in because we only really had the one controller. Well, now if another manufacturer supports it, we have that ability to swap the traffic signal controller, swap the APS system, swap the detector, because it's the cross compatibility is there, and part of that is this MIB ability. The other thing that we've seen recently, and while I don't have statistics like will be shown on the next slide, is we've seen the equipment prices decrease. As soon as we had multiple products for a particular item, all of a sudden the price starts to drop, and less cheaper price means that it's less taxpayer money. And as we've heard in other presentations, as the world of CAV comes around and we start needing to deploy connected vehicle technologies, we will evidently have to replace a lot of the equipment in our cabinet before the life cycle of the signal is over. These signals are designed, the steel itself is designed to last 30 years, but obviously we need to visit the cabinet infrastructure much more frequently than that. So having cheaper equipment allows us to hit more signals at once and get a broader deployment of this technology. The other piece that comes up, and as Mike mentioned earlier, is network security, which is much more than MIBS. Personally, I have found signal controllers sitting on public IP addresses. I don't know if they're in a test cabinet or maybe they were a university. You don't really know where they're deployed since a lot of that information isn't stored in the signal controller itself. But just the fact that that signal controller was resting on a public IP address just in the open world, if it was controlling a signal and I was a nefarious user, I could have put it to flash. I could have modified any of the parameters that are in there. So even without this sharing MIB piece, there still is a part of the network security that needs to go there. And even still, even if you don't even know what the MIBs are, you can actually bombard most modern traffic signal controllers to the point where they will go to a failure. All signal controller cabinets generally have a malfunction management unit that's in the cabinet, and sometimes you can make it lock up, either shorten a yellow, stop outputting a flashing yellow arrow, or you can do something to it to cause it to go into a failure state. And you don't have to know anything about the controller. You just need to know that it's an IP address sitting out there and you can bombard it with enough data that you can break it. The next thing that goes back to my university days is these advanced micro simulation models. All regional MPOs, they have a travel demand model. Well, that travel demand model takes into a lot of assumptions, especially on signalized corridors. I've seen some travel demand models where every signal in an entire agency's area is considered to be a 90-second cycle, and you give 45 seconds to each approach, and everything's permissive lefts. And as we all know, that's not how traffic signals work. And so as these MIBs get shared, the industries that develop those micro simulation models can start to ingest some of that data directly. The biggest reason why nobody does it is because having to input all of that data into a micro simulation model is a very time consuming task. I did one of those for the University of Minnesota. I put in about 1,200 traffic signals in a large scale model that modeled all of Minneapolis and St. Paul. And that was about 8 to 10 months of my life at the University of Minnesota, inputting all that information into the model. If there would have been some way to automatically ingest that data on a large scale, that would have greatly reduced the time. But then also, as computers just generically get faster over time, you can run those more advanced models with all that data that it's ingesting. And the final thing that kind of gets back into the competition is it increases that cross-vendor product compatibility. One of the things that's always a fun citizen complaint or question that we get is related to countdown pedestrian timer heads. So even before I joined the industry, you see that number counting down on the traffic signal and you think that it must know how much time is left. When in reality, all it knows is that the last time that the don't walk was up, that's how many seconds it took. If it changes for any reason, it can change that time again. Now, some of the manufacturers of that system have started to integrate fail safes for things like if the preemption truncates it, they'll remember it. but they still are not talking to the actual traffic signal controller. They don't actually know what the time itself is. They're waiting for something to pull it in to see what it is. So that's from the Minnesota DOT's perspective, and I guess I'll kick it back to you, Mike.
All right, thanks, Derek. Just a couple of slides left here. I know our time is running short. Next up, let me start my video. Okay, so next up is some information we have from Oregon DOT. Some cost savings they experienced initially just by moving to NTCIP for their message signs. The DMS manufacturers have historically been more cooperative about sharing their MIBs and allowing different systems vendors to implement support. And that's where Oregon DOT was able to achieve savings that you see here on this slide. And then more recently, as they were deploying ramp meters and their ramp meter vendor shared their MIBs freely with no restrictions, they were able to pursue different systems, central software systems that could support those ramp meters. And again, they achieved what they felt to be some cost savings there. So the gist of all this is, in today's connected world, the more data we have, the more data we can share, the better, the more true picture we have of the traffic situation. The MIBs drive better controller development and better integration with the central software, which allows us to all experience, I guess, a better bang for our buck when the agencies are able to choose the best solution and not be tied into proprietary solutions. So what can you do? If you think this is a good concept, you think it's good for our industry, please go to freethemibs.org, look at some of the additional information we have. And if you're really committed to this, then help us spread the word and use social media and others, and perhaps even sign up as an advocate for Free the MIBs. And with that, I'm done, and we will open it for questions for either me or Derek.
Okay, thank you, Mike. At this point, since we're running a little bit short on time, I'm going to ask that if you guys have any questions, you can put them in the questions and answers. And if Mike or Derek could type out the answers in the chat box there, that would be helpful.
Yep.
Now we have a word from our platinum sponsor, Temple.
Hello, ITS Georgia. I'm Forrest Temple with Temple Incorporated, coming at you virtually from the Temple booth. I wish we all could meet in person, but these are strange times we're living in. And I hope you all are staying well and staying safe. I want to thank you for allowing Temple to be associated with ITS Georgia. It's a great organization. And with this being the first virtual conference, the topics that the team has put together are very exciting and interesting to all of us. I want to thank you for everything you do for the state of Georgia. And I wanted to encourage you to reach out to any of us at Temple Incorporated for any needs you might have during this time. And I hope you have a wonderful meeting. And until next time, thank you.
Okay, our next panelist is Lee Ensminger. Mr. Ensminger began his career doing field work, collecting and cleaning data for various transportation agencies. He has since understood that field data includes a huge variety of incoming data streams, and over the following 12 years, he has worked to find ways to bridge the data gap between the field and back office systems. As a GIS IT project manager, he leads teams that seek to understand core strategic objectives within an organization and deliver projects that transform raw field data into valuable insights to help meet those objectives. And Lee, I'm going to pass it over to you.
Okay, thank you very much. And I'll share my screen. Okay, so hopefully that's up for everybody. Thank you very much for the introduction. Certainly appreciate it. I'm Lee Ensminger, and I'd like to talk to you a little bit about a project that we worked with our partners at the Pennsylvania Turnpike Commission, implementing a GIS as part of their overall intelligent transportation initiative. So I'll start kind of with a high-level overview here. At the core of this and at the end, this is really about a suite of web applications that we were able to create for them. These are user-facing, web-based applications, but really these are supported with a layer of data and processing that goes into that. So what we're talking about here are various APIs, internal data, external data, real-time data, near real-time, and certainly static data as well from things like maintenance districts or counties, things like that. And so by bringing all of this data together and processing it in such a way to either enrich the data and tagging pieces of data to make it more relevant and more valuable, or filtering unneeded data out of the stream to deliver only that data that's really value added and is really useful to push back up into those web applications. All of this is ultimately supported on a foundation of a geographic information system, or a GIS. So why would we do this initially, right? One of the challenges that we had there, again, working with our partners at the Turnpike Commission, was we had a lot of data available to us, but not a lot of insight, right? We weren't getting a lot of value out of that data. There was also a substantial information gap between our various users. So that specifically and especially comes into play during incident response activities. And as data is coming in very quickly, things are evolving very quickly, and a lot of folks have are working off of a different set of data, all of which is outdated, right? So we had this information gap that was problematic. And lastly, there was really a lack of analytics to better support after action reviews and things of that nature. And what I mean by analytics in this context is, again, that insight out of the data, instead of just looking at a raw table of any incoming data, what does that actually mean? And what are you actually able to get out of that? So we'll look a little bit here at, what this kind of looks like architecturally. You can see there at the top, we're kind of funneling in all these various pieces of data. We're bringing data in from, weather data in from the National Weather Service, AccuWeather, data in from our dispatch database, Traffic Operations Command Center, bringing data in from the ATMS, including work zone data, road closure alternatives and detours, telematics information, Waze data, speed data through INRIX, tolling locations, and some of the activities related there, social media, bringing all of these things in and pushing them into that GIS. If anybody's familiar with geographic information systems, this looked like a relatively typical implementation. We had a portal, we had a SQL Server database behind the scenes, a standard kind of Esri implementation. We were also leveraging this GeoEvent server and ArcGIS server that really allowed us to kind of do that processing of that data. We're able to funnel this data in very quickly. So, for example, some of the information that we're bringing in, for example, from Waze, we were able to, filter that data out spatially before pushing it along. So when we grab that, the API from Waze, we actually get Waze points from across the state of Pennsylvania. Most of that's not relevant, right? So we're able to say, hey, if there's a Waze point that is not within 50 feet of our roadway, filter it out. I don't need it, it's not valuable. So we're able to kind of overlay that spatially and push it out to these various endpoints. Those endpoints could be very many. We're pushing them out to at least 3. We're pushing them through Microsoft Azure out to mobile applications. We're pushing them out through to web-based applications and also to the geospatial cloud and ArcGIS Online. And I mentioned very briefly, but all of this happens very quickly, right? And that's really the key here, is that we're bringing this data in and processing it most times under 2 minutes for sure, usually more like 1 minute, sometimes less if we're able. So these things are happening very, very quickly as we're funneling this down, processing it, and pushing it out. Again, for those of you who may be familiar with GIS, those web applications at the front of this, where users really interact with this information, that is really only a small piece of the puzzle, right? Those are, off-the-shelf products that can be configured to provide some information. Really not much really special there, right? The real kind of special sauce here is that platform that facilitates that intelligent content delivery. That delivered content puts accurate data right into more users' hands. It does it faster and does it more consistently than it had prior to. So with those two elements, along with several other initiatives that the Turnpike was implementing at the time, we were able to help reduce major incident response times by almost 20%, which is substantial, right? That's quite a bit less time that the road is closed or otherwise hindered, or that responders are out there in harm's way. Right? So I would be a bit remiss here if I didn't mention the kind of holistic approach that goes into this. A lot of times with this technology, it's very easy to just throw technology at problems and kind of see what happens, especially when you begin to think about some of the emerging technologies and things like artificial intelligence and machine learning and data science. It's very easy to kind of become lost in that. And so one of our major lessons learned here collectively was it's critical to start with that organizational understanding and really have a thorough knowledge of what is actually driving the organization, right? And what are those major strategic drivers that the organization has identified, that this is what we care about and this is where value is in our organization. Once with that understanding, then we were able to take it down to the next level and identify key indicators that are really effectively specific problem statements. Those problem statements, for example, reducing incident response times, right? That's a KPI that we were working towards. And as specific as we can get with those things, obviously the better. But beginning with the end in mind, right, and beginning with the problem in mind is really where we're able to actually identify what needs to be done, assess the technology landscape at hand, and actually build a solution that speaks specifically to that problem. When that solution is deployed, right, it certainly can't end there. As the organization evolves, as those KPIs evolve, it's critical to evolve those solutions and continue the conversation with our customers inside the organization and say, is this still working for you? Is there new data out there? Has the problem changed or been modified? Is there old data that needs to be pulled out? And continuing to make sure that these things that were relevant stay relevant, right? So we'll look a little bit here at some use cases here, and specifically some of the things that we were able to build. Again, what this is really all about is that platform that facilitates some of these things. So this isn't one specific product or one specific thing that we were deploying here. This is a platform with multiple kind of value adds coming out of it. So this is one example, in wintertime operations, the maintenance personnel, when the snowplow trucks are out there clearing the roads, an important metric for them is how long does it take them to run those routes, right? Because each truck runs a specific route. How long does that take? And it depends on the tonnage of salt. It depends on snowfall rates and several other factors. But they ultimately did not have the information at hand. They could not, there was no way to know how long it took these trucks to cycle through. So we were able to grab the telematics data that was coming in, I think every 30 seconds or 1 minute, and apply some spatial algorithms to that as it was coming in and generate that information on the fly. So as a result, now the manager is able to receive a report after each snowstorm that says, here's all of the trucks, here's the plate number, here's all of the cycles that they made, and here's how long it took them to make each lap. Which is really, again, that's once he has that information, he's now able to go and, tweak his program and, work that KPI up or down as he needs, because he now has the information at hand. Here's another example. I just read a report the other day. It said Pennsylvania had the 3rd highest roadkill rate in the country. I forget where I read that, so don't quote me on that, but I think that was the statistic. But either way, it's a substantial issue, right? So we were able to grab information out of the incident database through the Traffic Operations Command Center and deliver a tool that allows managers to look at the data spatially, as well as across time as well. And so with those two things, we're able to identify some patterns and things like that so that they're able to more effectively deploy those countermeasures. And as a result, they're talking about things like installing fences, installing tunnels at certain locations based on this information, because we're able to pinpoint exactly where these incidents are happening. This was I think our last sort of use case here. This was a mobile application. I mentioned previously that, about that information gap, especially around field personnel. And this really kind of changed the game there for them. This pulls incident information out of the dispatch database again and delivers it here. Prior to this application, all information about a particular incident was funneled through email chains, text messages, phone calls. And so that's a great example where everyone has a different piece of data about the incident and it's all old. And that's painstaking in an incident response, in an emergency situation on the roadway. So with this application, as soon as an incident is created, it lands in mobile application. Users get a push notification. So, when you get a new email and it pings your phone, that's a push notification. So when a new incident happens, it comes in, lands on users' phones, and they get a notification. They're able to configure those so that they only get that notification for instance they really care about. So nights, weekends, they're receiving the information they need, either based on the type of incident or the location of that incident, based on their particular role in the organization. So this was really substantial. And one last kind of key feature here is that folks in the field who are actually on the scene responding, these are maintenance personnel, things like that, are able to grab a photo of the incident, load it back into this application so that anyone who's using this application can see the photos about the incident. And a picture's worth 1,000 words, and that goes a long way in communicating from the field to the folks in the back office exactly what's happening as they're trying to coordinate the response and things like that. And one last slide here quickly is, how does this fit with ATMS and other similar platform type solutions? At this time that we were implementing this, the Turnpike was also implementing an upgrade to their ATMS solution. And we really had to kind of learn how these two things would kind of fit together, because there certainly is overlap, right? A lot of these platforms out there can do very similar things. But what we found and what made the most sense here was for the GIS to really be, complementary to the ATMS and be very targeted and very nimble, so that the GIS solution is, aiming at specific objectives versus a, management solution across various assets. We also found that, at least working with Turnpike, there was access issues to ATMS, again, especially with folks in the field, and those were more easily able to be overcome through a GIS implementation. So we were able to kind of work through those issues in that way. So with that, I'll leave you there, and I think we'll turn it over for any questions.
Okay, thank you, Lee. At this point, and if you have any questions, make sure to put them in that Q&A box. Give it a few minutes. Okay, since there are no questions coming in at this time, anything else you'd like to add, Lee?
No, thank you.
Okay.
I appreciate it.
No problem. Thank you for joining us. So coming up next, the next session coming up is session 3, Farsighted, Research, Data, and the Future of ITS, which begins at 3 p.m. today, Eastern. Thank you all.